Okay, let's take a look at this. So over here we have this sort of question, and this deals with recursion. You can ignore the kind of header over here because it calls change. You can just completely ignore that. It doesn't really matter here too much. So the point of this question is to get all the unique possibilities that each of your amounts or each of your coins can create. So if we have 2, 5, and 3 as our coins, we can like how much basically total money can we create from selecting either 0, 1, 2, or 3 of these coins. So over here I can select none of them and that'll give me 0. I can select 2, 5, and 3. And then I can select or not and, but rather 2 or 5 or 3, and I can select a combination, so 2 and 3 together, and then 2 and 5 together, and then 3 and 5 together, and then all of them together. So yeah, this is what ends up happening. But this question also asks for unique n. So we need something unique. We need unique numbers. And you can ignore this part. That doesn't really matter too much for this question. So it needs to be sorted also. I don't know if I said that. Yeah, sorted order. So the thing about this question is essentially we need this list to be in a sorted order. So essentially 0, 2, 3, 5, 7, 8, and 10. But then we also don't want any duplicates because in this one we had 5 twice and we don't want that. So that's what this question is asking for. There isn't too much else that's interesting over here, but I guess we could get started with this. So A, B, C, and D. So the idea here is we have to do this recursively, and we're already given some tools in order to deal with this recursively. So firstly, we actually already have a recursive call thing happening over here. So we know we're going to get a recursive call somewhere. And then we're also, this is like our return line, and this already handles sorting for us, so we don't need to do that. But it hasn't handled the unique n part yet, so we have to deal with unique n somehow. And base case is over here. So I'll just write down the base cases here, and then we have our recursive case, and then we have connecting it. Yeah, that's not very neat. Let's connect. So the way basically that I dealt with this when I took this midterm was kind of breaking it down. So we know that the first coin over here, we have coin is equal to coins of 0. So if I just take the first doc test, which I think is the only one that's important here, then if I take coins of 0, what I'm going to take is the number 2 or the integer 2. And then amounts is probably going to be, well, it has to be a smaller version of coins. So by that nature, it would probably make sense to call coins of 1 onwards. So we're kind of skipping everything but the first. So in the first doc test, we end up getting 5 and 3. Now, like, this was just the kind of guess I made. I didn't exactly know what to do with it just yet. But I did see we had 2 different places over here. And there's also addition over here. So we know that this thing on the right has to be a list because it's in the list comprehension. So to get this to add correctly without any errors, the part C also needs to be a list of some sort. So I know that C has to form some sort of list, whether that's my own list comprehension or something else. I also know that amounts will eventually return a list in the end. So that might be helpful for later. I might be putting rest in because that's my recursive call. Maybe. Or I might be doing something else. So like it might be a list comp. Or just, putting in the list myself. So if I take coins of 1, let's just take a look and see what possibilities we have from here. This is the recursive leap of faith, basically. you're just calling the recursive function. So you're calling amounts with the smaller input, and you as like the person writing the code are supposed to just figure out what this is supposed to output, and you don't kind of need to trace it through. You just kind of assume that the output from calling amounts with this input will give you the correct output. So in this case, I can choose to use none of the coins, which will give me 0. I can choose to use one of them, which is 3. I can choose to use the other, which is 5, and then I can choose to use both, which is 8. And there are no other possibilities. So also, I want to eventually get a list that looks like 0, 2, 3, 5, 7, 8, and 10. And like, we're already somewhere there. We see that we already have a 0, 3, 5, and 8 in here. So all we need to do is just kind of figure out how we need to get to this, like how we can fill in the rest of these gaps over here that we haven't gotten yet. So I also know that for this first stock test over here, coin is coins of 0, so we're calling the 0th element, which is 2 in this case. And there's some way I can connect 2 of these numbers to get the remaining ones, which is if I add 2 to each one, I'll get 2, 5, 7, and 10. And notice how we do have a duplicate here, but then we can deal with this somewhere, or we have to deal with this somewhere else. But other than that, we also have 2 here, and then we have 7 and 10. So now we have all the numbers. So I know I have to find a way to connect the recursive call and this first thing over here. And we see on this part at the end, we have a k plus coin. So we know that coin has to be used somehow in this list comprehension. And we're adding that to k. And, you know, there's a sort of like relationship here. We're adding something to k. And we're adding coin, which in this case is 2. So this would probably be for like k in whatever this thing is. And over here, recall that when we use rest, we called amounts on coin of 1 onwards, and that returned this list. So this would actually just be rest, because rest would already have this result. So in B, I would put coins going from 1 onwards. So now I'm done with part D and part B, or at least I'm done with the current implementation yet. I still haven't dealt with the duplicate yet, and I have to deal with that somehow. So I'm going to deal with that later. But just, yeah, remember that like the recursive leap of faith is just assuming that you get your answer that you want, and it's not sort of tracing through each and every call to make sure it's correct, because that's not necessary for recursive solutions. All you need is those 3 steps that I've mentioned earlier on in my somewhere in my guide. So you can go look at that, or look at course website. That is also really good. But yeah, that's a recursive leap of faith. That's, in my opinion, the most helpful concept to grasp for recursion, and it's also the hardest thing to grasp, but it's definitely super important. So if you haven't gotten used to that yet, please do. Anyways, for C, well, I want to be adding this list over here, the 0, 3, 5, 8 list, together with this new list where I'm adding all like my first coin with it. So in part C, I can just put rest, because rest will end up giving me this 0, 3, 5, 8 thing, because that's like the rest of the combinations we get from coins. And then k and rest right now will give me 2, 5, 7, 10. So when I add them together, we'll end up getting 0, 3, 5, 8, then 2, 5, 7, 10. Oh god. Writing at the edge of my tablet is not really the best thing. It starts getting a bit jittery. But notice how we still have that duplicate, so I need to handle it somehow. I'll return to the base case later. The cool thing about recursion is you can deal with at least the recursive case and the base case in completely independently of each other. They don't really matter too much. But the connecting the recursive calls together is typically easier to do when you know what your recursive calls are, but that's not necessary. Anyways, there's only really one place to deal with dealing with duplicates, and it's in D. Because we know in list comprehensions we can use the if. So if k plus coin is in my original resting, which in this case, if we get 3 plus 2, and that's already in rest, I'm just not going to add it. So if it's not in rest, and that should work. Because now when we do this k in rest, if k plus coin is not in rest, then what ends up happening is we get 2, and then we skip 5 because it's already in rest, and then we get 7 and 10. And when we add them together, we end up not having this one, which gives us all the numbers we need. Remember that it already handles sorting for us, so we don't have to deal with that ourselves. Now for A, if we have not coins, which in this case, the only way to get to not coins is when you have coins as an empty list, because calling a list comprehension like that on an empty list of some sort will also give you an empty list, or at least calling it on an empty list will do that, and calling 0 onwards. But when you have an empty list, you know that you have no more coins, and the only possible choice when you have no coins is to return a list of 0, and that's because all the possible coins, remember that amounts returns a list of numbers, and the only possible thing you can do at that point is to just, like, when you have no coins to pick from, the only amount you can create is 0 rather than an empty list. Another way to think of it is that, well, if we're calling rest, or if we're calling coins over here, or amounts on this value of coins, there's actually no way to extract 0. Because 0, you can't really get 0 from an empty list unless you explicitly create it. So that's why this first part needs to be 0. But, I mean, if that doesn't really matter, it doesn't really matter if you understand that as much as understanding the recursive leap of faith. I think the recursive leap of faith is by far and away the most helpful learning tool for this problem. So make sure to go and understand this problem and actually truly understand what it means to take the recursive leap of faith, because it's seriously helpful.